get started yet.
It says live.
And now we are live.
Yay.
Hopefully. All right.
Welcome back.
Welcome back to the next installment of the Programmers for Engineers and Scientists Extra Help Session for week 6. All right, so what we might start off with is go over the hard quiz questions like we normally do. And then from there, we can go on to the assignment, and then we'll go on to the content for this week. Does that sound good?
Mm-hmm.
Or do you want to break it up any different way?
Sounds pretty good to me.
Good work. All right, so the first question I've got here. Sorry, you filled in the response. Oh, got rid of it. Cool. All right. So this question was done a little poorly. So this one we'll start with. I'll just move that across. Put the question there. So this question involves pointers and functions. So I'm going to do this using the box and pointer diagram. And for some reason, and I need a new layer. Cool. All right, so first things first, we're inside main. Let's go this color. So this here is main. Now, we first declare the variable a of type int, and it has the value 5. Don't do that to me. Why is this being silly? Sorry. I might have to go to the old program again.
It's a very wonky box.
It is. I've got everything in the wrong place. I'll move it in a sec. And we've got b, which is 10. And then we call this function. So let's draw another box for my other function. So we've done the first step. We've created an int with 5 in it. And then we've created another int with 10 in it. First one's called A, the second one's called B. Then we go to myfunc. So this is now in scope. So we create 2 more variables. Our variable is A, and it's an int, and B, and it's an int. Now, this may be tricky. These have the same names, but they're 2 separate variables. So while I'm in scope here, this memory still exists, but this name does not. Okay? So I pass A into this variable A, so now it's 5, and I pass B into this variable, so now it's 10. I change the value of A to 10. Now, that works better. So I change the value of A to 10, and I change the value of B to 3. Yep. Once I've done that, the function ends. So now we go back, and main is in scope, and this is gone. The memory 3 and 10 is still somewhere, but we've got no reference to them. So then I get to the next line, and I print A and B. So what's going to print for A will be 5, and what will print for B will be 10. So this function here didn't really do anything to main. It didn't have any side effects to main. And that'll happen sometimes. You'll have functions that will do their own thing for their own purpose, but won't return anything. So the answer will be 5 and 10 for this one. Any questions?
Hi, Matt.
Hi.
I could understand what you just taught now,
Yep.
but considering the same question, can you just show how to pass by reference?
Yep. Let me see if that's one of the questions. Hopefully it is. Yep. That's one of the next questions. So I can do that. Let me see if I can find a similar one. I'm pretty sure Josh is not a template, but S1. I can't preview these. That's the only problem.
You can't?
No.
Oh, that's strange.
Now there was just in case you're wondering, Ella, there was a question that was wrong on the quiz, and it's been fixed up. All right, so pass by reference. All right, so I've got an example here. Open it. Get rid of that one.
Damn, it wasn't the one I got wrong. Just went and checked my score to see if it had been fixed.
Oh, okay, this one's not a very good question. Okay. Sorry, I'm just going to try and find a good question. Okay, I think this one's a good one. Come on. Okay. I think I've opened the same question multiple times. Okay, maybe I'll just make the question. What I'll do is I'll take this question and change it so we pass by value. So let me open up just Notepad. So we've got this here, and what I'm going to do is change this to a pointer, and this to a pointer, this to a pointer, this to a pointer. I'm going to change this to the address of A, the address of B, and then dereference both of these. Okay, so this is passing by reference. So in this example, we now have...
That would just make it print 10 and 3, wouldn't it?
Yes, but Ela asked for an example by passing by reference.
Sorry, I wasn't here.
That's all right. So I really don't. Okay, so here we've got main again. And we create two variables. A, it's an int, and it's got the value 5. And then we create B, which is an int, and it's the value 10. We then go to our function, and we pass two values. So first we create our variables, which are A, which is an int star this time, and B, which is an int star. So they're both pointers to ints. Now the difference here is that now we're passing the address of A and the address of B. So before, so this is my func here, we were passing values, so passing the 5 and storing it into the A because it was an int. But now we're going to send the address of A. So now what we've got is this link between these two functions. So even though I can't see A and B, their names, I can still access them and change their values because I've passed their reference. So now I get here. So this here is dereferencing. Because it's on the left-hand side, we want to store whatever this results to into the place that this is pointing. So we're going to store 10 where A is pointing. So A is pointing here, so this becomes 10. The eraser isn't big enough. Okay. So this becomes 10, and then our next line, this 3 gets stored where B is pointing. So this now becomes 3. Does that make sense? And then we return, and then we print 10 and 3. Happy with that, Ella?
Yeah, thanks.
Cool. All right. So let me have a look at another one. Try to find one that's different. I think I opened the same ones up multiple times. Okay. Let me open this one up. Sorry, just all these questions. Yep. All right, so the next question I've got here is this one. This is a good example. So this is a code fragment, but we can assume the top part is main or some other function. It may not be main. So let's draw another box. And the function we're currently in declares an int, is the first line, and we call it x, and it's of type int, and it's got a 5 in it. We then create a pointer to an int, which is called p, and it's of type int star, and it points to x. Yep. We then call this function mult, which I think is multiply. Called mult, and it creates a variable called p. This is a separate variable. And it's called p, sorry. And it's of type int star. And here we pass p. Now the value in p is a pointer to 5. So we pass that reference. Sorry. I don't know why it's doing that. And now we've got this link. Okay? Because we pass this value in, we grab the value, which is this link here. And it's a reference. Okay? So this line here is what it's grabbing. So now we go in here, and we are dereferencing p times equals 2. So we can think of that as being dereference p equals dereference p times 2. So this here is 2, obviously. This here is times, and this dereference is going to be 5 because it's on the right-hand side. And so we go grab what p is pointing to, which is a 5. So we've got 5 times 2, which equals 10. and then we store it where P is pointing. So now this value here changes to a 10. So when we print this out, we now get a 10. Does that make sense? It's actually a really good example. Yep. All right. I've got enough. Why is that not working? Okay, so next, what I'm going to do is look up what was the pass rate for this one. This one was about 40%. So I'll just quickly look at this one, and then I'll get Josh to take over and go through a couple other ones. This one's very similar to the first one. I'm just showing you because you need to be careful with this overloaded operators. So here, once again, we have main. We have x, and it's an int, and 5. Call our function, which is called mult. We create a variable called num, and it's of type int. So here we've got our int, which is 5. We then call this function and send this 5. So this is a number. So we're passing by value. When we get here, so we've got the 5 in here. Once again, we've got num star equals 2. Now that star means multiply. So we've got num equals num times 2. Okay, so this becomes 10, and then the function ends. And so we print 5. Now, as I said, you need to be careful with your multiplications and pointers. So if we have a pointer and we want to dereference it, you may end up with things like x times dereferenced y. What's a good practice is to put these in brackets so that you know that this one's referring to a pointer. And same if you had a double pointer and you wanted to dereference it, put them in brackets just so it's clear. Okay? So multiplication can sometimes get confusing because you're using the same operator. All right. So, Josh, do you want to get up question W6M3?
W6M3.
Yep. This
Sure.
one. And the other one, while you're there, just so you save your time, is W6F4.
F4. Awesome. Cool.
And I'll pass the screen on to you. But you'll need to share your
No
screen.
worries.
And then I'll just move everything around, just draw properly.
Yep. All good. Just getting it on the screen. Cool. Is my screen showing?
Not yet. Give me 2 seconds. Now it is.
Okay. All good.
Yep. Yeah, you're fine.
Is my...
Yep.
Oh, I was waiting. Sorry, I thought I wasn't on. All right, so we've got a question here. What line of code does the following image represent? So we can see we've got our memory diagram here. Just having a look at our diagram, we might start with this first box. So we've got a variable that's called float a. The type is a float, and it's got a value of 3.26. And then the second box that we've got here, we've got a variable called pointer a. We can see that it's a pointer to a float, and we can see the value here. This means that pointer a is pointing to our float a variable. So when we see these things, that's what that means. And you've seen this in the lab as well. So now going through our responses, we know that if we want to assign pointer a the address of float a, we need to be thinking about what sort of operators we need to use to do that. And we know from what we've been doing in the labs, when we see this ampersand, this means address of. So whenever we see the ampersand sign being used, we're talking about the address of. So we use this with our scanf statements all the time. We started using this more since we've been using pointers. So if we want pointer a to be equal to the address of float a, it's kind of exactly how it sounds. So what it would look like should be something like pointer a equals the address of float a. And again, it's exactly how it sounds if you're reading it out loud. So going through our responses, we've got the address of pointer a equals float a. Now we know that that's not correct. We've got pointer a equals asterisk float a. So we know that with this asterisk here, we use that to dereference pointers. We use it to declare a pointer, or we use it for multiplication. So we can see that float a is just a float variable. So asterisk float a isn't going to do the job. We'll go down to D here. So the address of pointer a equals the address of float a. We can see that that's not going to be correct either, because we want to assign pointer a the address of float a. And then going down here, pointer a equals float a. Straight away we can see we're not assigning the address of. So from this, we can see that C should be our answer. And remember with this stuff, if you just read out how it sounds, that's going to be pretty much what it should look like. But the biggest thing to remember is the address of is the ampersand. Cool. Does anyone have any questions on that? Awesome. So I'll go to the other question now. F4. All right, so what is the output of the following C program? So we've got an include up the top here. We've got a function prototype. So the function name is func. It takes in an int pointer and an int, and it doesn't return anything because we've got a void here. We've got our int main, all the stuff that's inside there, and then we've got our function down the bottom, the definition of the function. So just going through from the top, we're declaring a variable x, letting it equal 5. We're calling the function, we're giving it the address of x and the number 2. So just by looking at this when we get to this stage, when we get over to here, we can actually see that const int is different to int. So in our function prototype, we've said that this should be an int pointer, but what we're actually saying down here is this is a const int pointer. So these two things are actually different. And if we try to compile this, we'd probably get an error showing up. And by looking at the responses, this will not compile. That's sounding pretty good because, again, we're saying up the top in our prototype that this should be an int pointer. We're saying down here this is a constant int pointer. So because these are different, we're probably going to get an error. So that's why we can probably assume that it's going to be this program will not compile. Of course, if we wanted to, we could always just run this, put it into PuTTY, give it a run and see what happens. But that will be what happens. We will actually get an error and the program won't compile. And another thing that will probably happen is if you do try and modify the constant you'll probably get an error showing up as well, because we're saying it's a constant, which means we're only allowed to read from it. So we sort of touched on this in the stream last week. So if we're trying to modify a variable that we can only read, we'll probably get an error when we try and compile. So we should have this program will not compile as our answer. Does anyone have any questions on that?
Josh, I have
Yeah.
a doubt. Generally, I've seen like when we are passing using reference, like pass by reference,
Yep.
what I've observed is we always use void function. So
Yep.
is there any specific reason?
The reason for that is before we learned about pointers, we were using functions that return values. But now that we're using pointers, we know that we can actually modify these values using pointers. So you know how we talked about how can we return more than one thing from a function? We use pointers. So there's no reason. You can definitely make these return integers if you want to. But normally what will happen is if you do need to modify a variable and you're passing by reference, you're probably going to modify that variable simply because it's being passed by reference.
So I'll just add to that. So you'll see with a lot of functions that when they're passing a lot by reference, they'll either return something new, so something that wasn't thought about before. So when you're passing by reference, you're usually trying to change something you originally had. So, for example, if I want to keep my original variable, but I also want to see it rounded, let's say. So I send the variable in and I get a rounded version back. But if I wanted it so that I round my variable and I don't end up with something back, then I pass by reference. The other thing that you'll notice a lot is that a lot of functions will actually not be void. It's a good practice to avoid using void in a lot of functions because you can use it to return an error value, which you'll see in a couple of labs' time. So as you saw with main, we return 0. So what we can do is we can return 1 to say this kind of error happened, 2 to say this kind of error happened. And the same with our functions. So we can, let's say we're doing some complex equation and we're passing by reference, but if it fails, it returns a 1. If it fails for a different reason, it returns a 2, and so on. So the return value, it depends what you need it for, but if you're not returning anything at all, sometimes it's good just to have it as an int so that you can return an error value. But the reason when we're avoiding the return and doing the reference is just to not confuse the two until later. You're seeing it a lot as void right now because we don't want to confuse you.
I was thinking about this for a while actually. If you have a return value anywhere within a function, even like multiple ones, whatever, as soon as the code sees a return, does that stop the function? Is that the end of the function?
Yes.
Yes.
So you should be careful where you use returns. A lot of people say that you should have one return. That's not good or bad programming practice, but it makes things easier. Your function should have a clear entry point and exit points. So if you've got returns randomly placed and they're returning all different values, then you haven't got a clear exit. So if you think of a function as a box, so if you draw your function as a box, where's my pen? Can't see the pen.
Have you got the screen?
Yep.
Good.
The inputs are all your arguments. The output is what you return. But you may return in different spots depending on what happens. But it should be clear that this will happen. So your return shouldn't really be inside loops, but they could be in an if statement because it's clear when the function ends is a good programming practice. But yes, you can have as many as you like.
Okay.
But you should know that there is a clear entry and exit point. So a lot of times you'll see a function written where it'll have returns if there's an error. So there was an error there, there's an error here, and then if it completes successfully, there'll be a return 0 at the bottom. Another way to do it is instead of having these, and you usually have macros to declare what the errors are. So 0 will stand for something, 1 will stand for something, and so on. Or you could have a variable, let's say int error number, and when it gets to the end, it returns the error number. And if it's 0, then it's fine. And the reason we use 0 as saying it's all good is for an optimization reason, because if we write our function, if func inside an if statement, we don't need to store the result because if it fails, it will go into here. If it doesn't, it will continue because if 0, it will continue. Does that make sense?
Yeah.
Cool. All right.
So Matt, like you said, we'll be always saying that the functions are void.
No, we won't. I didn't say that. I did not say that.
No. Like up till now, we have seen when we are.
So in future labs, you will have return values. For right now, because we're focusing on pass by reference, we're just avoiding the return just to not confuse the two.
Yeah. So if suppose I have to return the integer pointer, then how should I write the return statement as well as how should be my function type?
So you can return a pointer. So you can write func up the top. That's fine, and then your function will be the same, and then you can return an address or something like that. Now, you have to be careful doing this because these variables here, you have this reference back here. So you can do it, you just have to be careful because as soon as you lose this reference up here, it's gone. And you need to remember to free your memory, especially if it's outside of main. So if I do, int a here, equals 4, and then return its address, that's fine. So yeah, you can return a pointer, that's fine.
Mm-hmm.
You just have to be careful about it, which you'll see when we do arrays this week. I think this week, or I think you won't need to be careful this week, but the following week, yeah. All right. So I've got a couple of other questions. I just like this one because it's cool, and it takes 2 seconds. All right. So this question here, I'll actually blow it up a little bit. You know what's really annoying?
What's that?
If you blow this up, all your things get blown up.
You're using the wrong detonation. Like using dynamite or something.
Okay, so here we have W, and it's of type float, and it's got 10.5 in it. Then we create a pointer X that can point to floats. So we've got X.
Who wrote this question?
Josh.
That was me.
And it's pointing at the address of W.
That is
Then-
the most inefficient use of code ever.
Actually, it's not. This is how a lot of your file systems work. Obviously, this here is inefficient, but pointers to pointers to pointers is actually how your file system works. So it's actually a really, really good way of doing memory management. Okay, so here, we're pointing to here. And then here, we've got Z, which is a float, star, star, star. So basically, if you want to know what something can point at, just delete a star, and that's what it can point at. So a float star can point at a float. A float star star can point at a float star. A float star 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 can point at a float star star. All right. So now let's have a look at what each one of these would print. So the first one we have here is %f/n star star z. So if we're at z and we go one star down, we get to here. If we go another star down, we get to here. Yeah?
Yeah.
So that's not going to work because it'll print out an address. If we go star y, it's going to go one place back. If we go x,
I noticed
it's going to
that
print out this.
conveniently the very last one that we go through is the correct one.
They're randomized, the order. So that was, I didn't choose that. Then the
You kept
y,
on generating the question until you got it right.
yeah, exactly. And then the last one, it's one step back. Okay? But if we wanted to, let's change this question a little bit.
Well, what I was
We
going to ask...
all of these things would work. So, oof, didn't mean to do that. If I did printf %f, just to save some space, I won't put the new line, I could do star, star, star z, and that would print out 10.5. I could do printf %f star, star, y, and that would print out f. I could do printf star x as the answer. Oops, that's a z. I didn't know my letters. And our last one would be just printing it out. And I forgot the f, which would be 10.5.
So if you told X to point at something else, that would, like,
Okay. So if you told-
change the whole chain.
Okay.
Like,
so
they'd all
wouldn't
still
you-
be pointing at each other, but, like,
Yes.
if
So
you
if-
printed
if
out
I-
Z star 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 star, it would now be printing out the new thing X is pointing at.
So if I create a new variable, let's say float n. N's really bad. M, let's say. And
B.
it equals... No, I don't like B. 2.5. So now I've got a new variable called M, and it's a float, and it's a value 2.5. And then if I come along and go, I go X equals the address of M. Now all that changes.
Yeah, I know it doesn't change
This.
much in the memory map, but in terms of like what you can print out with these,
Now
it changes
now-
everything.
Now all of these would print 2.5. And so, as I go back to what I was saying earlier about memory, rather than having to change everything and where it is in memory, we can now just change the pointer. So now when we create a new file or a new set of systems, all of these are still intact and we don't have to change them. They point to the correct new thing. which is very, very handy, and it makes things a lot faster.
I also noticed there's an arrow there that's inside the box.
What do you mean? Oh, this is just saying that is meant to be at the box.
You should never draw arrows in boxes, Matt.
No, so these arrows are actually, because we're dereferencing, they are in the box. That's what I was trying to show. We're going back a step and looking what's inside the box. We're not looking at the address, so they actually should be inside the box when I was doing the dereference. So that's why you don't draw it in the box, because when you're dereferencing, you're actually looking into the box, not the outside of the box. Does that make sense?
Yeah. So Matt, the
Yeah.
last statement which you had written, printf %f 10.5, should
Oh,
that
whoops.
be?
Yeah. Well, that'll work. That's fine.
That's the way to do it.
It'll print 10.5. There's nothing wrong with that. It'll just
But
always
that should be a variable, right?
No, that's fine. That'll work.
Is it?
Yeah, of course. Is this a float?
Yeah.
Then it'll work.
Who knows? Maybe you declared it as a double.
No, I didn't, because I didn't put the.
Oh, and it's F.
Yeah, so it'll be 10.5f. But no, I can do. There's nothing wrong with me doing %d5. That is purely legal because 5 is a number. Having a variable there is just grabbing the value that's in there. So 5 is exactly the same. So we can write a number there. However, it would be kind of pointless because if this is a constant 5, it'd make more sense just to write it in the text. Because we've saved an operation. If that makes sense.
Mm-hmm.
But no, you can put just a number there. That's fine. Anywhere you can put a variable, pretty much you can put a number there. It's the same thing with your functions. So if I have a function call, say func int x as my prototype, and I want to call it, I can go func a, or I could go func 5. Because you've got to remember printf and scanf are just functions as well. They're all just functions.
So say that int 5, if you divided int 5 by 2, what would happen?
Which int 5?
Just you had an integer that was 5 or another odd number. What would happen if you divided it by 2?
In where? Oh, in here?
Just in C. Yeah. What is an odd number divided by 2?
So this would evaluate first, then it would store into the int. And what happens when we do that? It trunicates it.
Yeah, but which way? Would it return?
It trunicates it.
Would it return 2 or 3?
It trunicates it. It doesn't round it. It trunicates it. So if it's 2.9, it's gone. It's 2.
Excellent. I think you may have just solved my problem with the challenge question.
Really? Okay, that's odd.
I'm sorry. You already know that I'm doing it a weird way.
You're on the right track. Now I'm confused at what you're doing.
Well, I can't use the % sign to figure out whether it's an odd or even, so I got to figure out a mathy way of doing it.
There's a lot simpler way.
Mm.
But I'm not gonna tell you till next week.
I'm just gonna laugh at my awful code.
I want to see how long it is.
It's so long. And every time it returns an error, it's like error in line 5. I'm like, oh, thanks, that helps a lot.
So, 2 people have already solved it as well.
Have more people solved it?
What? Yeah, a couple of people solved it.
Okay.
It's not impossible. Once you work out the trick, it's fairly easy. Which you've worked out the hard trick, so you've just got to work out the odd and even stuff.
The next bit is writing all the labs without semicolons.
Which could be done.
Suppose so.
All right.
You're very big pain. Hey.
It would be a pain. All right, so let's have a look at this last. Oh, do you want to do the last one, Josh?
Sure. What?
P8.
P8. Getting it on the screen.
No, don't do that.
No?
No,
What?
not me. Talking to myself.
Okay. Alright, so I'm just going to share my screen. Cool. Are we in?
Yep.
Awesome. Alright, so what is the output of the following? I'm just going to draw up some boxes here.
I actually prepared boxes and that, so I haven't used them.
So, look how good my boxes are, though. I mean, they're pretty good. All right. So on our first line here, we have a character called var1. Oh yeah. And we're giving it the value of the letter J. We've got another one over here, which is var2, which is a character again, has a value of K. Right, the next line here, gonna need another box.
I forgot to put an email on.
Alright, so our next thing that we have here is we're having a character pointer, so we're calling it pointer1, which is a char star, and we're assigning it nothing at this moment actually. So right now we've just declared it, we haven't given it a value yet. And finally, we have another one, except it is called pointer2. Right, so on the next line here, we're assigning pointer1 the address of var1. So what we're doing there is, I don't think there's any arrows here. We're saying that pointer1 is now going to point to var1, so to the value of j at the moment. And what we're saying for pointer2 is equal to the address of var2. So just ignore my horrible paint skills. Cool. So on the next line here, we're saying that this is, when we're using it with pointers, we're saying this dereferences the pointer. So what we're saying is instead of talking about pointer2, we're actually talking about what pointer2 points to. So right now, pointer2 is pointing to var2. So essentially, when we say dereference pointer2, this is the same as just saying var2. So remember, whenever we say that asterisk, used in this context, we're saying that we're dereferencing that pointer. Looking at the other side of that as well, we're doing the same thing for pointer1. So we're dereferencing pointer1. So essentially, dereferencing pointer1 is the same as just saying var1. So what we're effectively saying here is var2 equals var1. So what we're going to be doing is we're going to be getting var2, which is this k, and we're going to assign var2 the value of var1, which is a j. So what we're essentially doing is we're getting rid of this guy, and we're going to make him into a j. Cool. So this is what we're looking at now. We've said dereference pointer 2, let that equal to what we have when we dereference pointer 1. And then we're going to print out 2 characters. So remember, dereferencing pointer 1 says we look at pointer 1 and we look at what it's pointing to. So when we execute this, or when we see this, sorry, this is the same as just saying var1, which we know is a j. And var2, of course, we know how to do this. This is just simply j. So the answer should be j space j. So something to be very careful of when we're dereferencing. And just in general, being careful when you see these asterisks, try and really work out what's happening, especially if you have multiplication and dereferencing. It can get really confusing. Does anyone have any questions about what we've just gone through? Nope. Do you want to add anything to that, Matt?
No. I'm sorry, Josh.
It's just not fair. Not fair. They're pretty drawing. Maybe I'll use paint and make it pink.
The symmetry in that first box is awful.
It's not that bad. I mean,
Should be pixel perfect, Josh.
wait, okay.
They'll revolt against you otherwise.
This is true. Wait, how's that?
That was giving me a headache.
There we go. Oh, perfect.
Okay.
Cool. What do we have next?
Alright, so next I just want to
There we
quickly go over assignment 1. So, just a couple of things that I want to bring up about assignment 1. Firstly, this thing. This is an individual assignment, and so we weren't too harsh on this time, especially where you could see students actually knew what they were talking about, but it is an individual assignment, and for individual assignment, plagiarism does include the case where 2 or more students work collaboratively on the assignment. So it's just a warning for the next assignment. The other thing that I will mention is, firstly, test cases. So it's a good idea with your program to try and make your own test cases up and test your program thoroughly. There's a lot of students that just tried the cases that, these 3 cases that were here. You should try your own cases and make sure it works. Because, yes, 60 might always work because you've hard-coded 60 in, but nothing else will work. So a good idea is to write up a list of test cases and test a whole bunch of stuff until you're happy. We will do testing as one of the last things we do in this subject, and so you'll learn how to write what values to choose for testing and stuff like that, but you should be testing it. The second thing is that I noticed a lot of students did just brute force the solution in a lot of cases. So in week 3, I think it was, we introduced the flow diagram. Whenever you're coming up with a solution, especially a complex bit, so for something trivial like a simple function that has maybe 3 lines, it's not worth drawing a flow diagram. But if you've got a couple of loops happening, say a couple of while and a couple of for loops, draw the flow diagram, as you may be able to find a simpler way to write your program and optimize it. So for when you've got looping especially, draw the flow diagram, because you will be able to improve your code and make it a lot faster and a lot more readable.
What do you mean by brute forcing?
So just trying everything until it works. Does that make sense?
Not really. I don't see how that would work.
So it's for this, you've followed the steps, and if you haven't got the step, you keep trying everything you've learnt until it works. And we saw a lot of cases where people have done that because they've given up on their brute forcing.
Like, what would an example of that be? I'm just trying to
Trying a
figure
while
out
loop.
whether I did any of this or anything.
No, I don't think you did. But trying a while loop and then changing it to a for loop and then changing it to an if statement and then changing all your variables around. So try variable 1, try variable 2, try variable 3 until it works.
That sounds like a lot of work.
It does. It does sound like a lot of work, and that's why you shouldn't do it that way. Okay? So you've probably heard of brute forcing a password.
Yeah.
Basically the same thing with code. Sometimes brute forcing is one of the solutions for solving some coding problems, but rarely. Double pointer, sure. Okay. All right. So, now you made me forget the other things. Most people use types pretty good. One thing I did notice, however, which is not too good of practice, everyone did this. They declare all their variables up the top and then use them throughout the program. Now, if you've got things that are used throughout, which most of them were, you include them at the top. But your iteration variables should not be declared at the top. So I saw a lot of this. Int I, float j, sorry. Float j. Now, this, for a trained programmer, is firstly confusing. And also, so the reason it's confusing is usually when you use I and j together, you're usually referring to this. So you're talking about a for loop within a for loop because the I is usually here and the j is usually here. And then you'd have k here if you needed another loop. And so when you see the iteration variable, I, j, k, n are very special variable names that most programmers will know the meaning of. N represents the size, I is an iteration variable, j is an iteration for double for loops, and k is for triple for loop. So if you see any of these variables, I, j, k, or n, you know what they're talking about. That's why I didn't want to use n before. So how would you do it instead is if I had two for loops, and one is going to do a floating point for loop, and one's going to do a integer for loop. The first thing, if I have an if-else statement, if else, let's just say if a equals 1. And then inside this, let's move this up. Where's the movie thing? Moves everything around. Oh, there it is. Okay, so if I have that up there, and then I have my else statement down here, and I have to put a for loop here. Okay, and I want I to equal 0, I less than 4, I plus plus. And then I want to create another for loop here, but this time I is a float. Up here it's an int. Let's say 4.2, I plus plus. Actually, let's say I plus equals 0.1, let's say. Where would I declare I? So good practice would be to declare I next to your for loop. So then I'm using the iteration variable to say this is a for loop. This is an int, this is a float. They're in scope between these braces. So we don't need to create int I up here and float j up here. Okay? I is not running through your whole program and float j isn't running through your whole program. It's only used for a loop. If you've got multiple loops with the same type, int I should be declared at the top of the first one. Now, if we didn't have this if-else statement, the other thing we could do is put these into scope. So I can just do this myself. I can put this into scope without an if-else statement. And now I've got a float I and an int I just for this for loop. And then once I'm finished with the for loop, the I is gone. Does that make sense?
Yeah.
Yeah? Okay. So I just want to be clear on that because I saw a lot of people doing that. Now, what else was there? Most people formatted it pretty well. I'll let Josh go on with more because he is really about them comments. Josh,
All them comments. Yeah.
want to mention anything that you noticed a lot of people doing in the assignment?
Yeah, I think.
Where
So
they lost a lot of marks?
yeah, I'm trying to think the most common ones I saw. So yeah, touching on comments, it's really important to make sure your comments are useful and meaningful. I saw a lot of people who were just commenting on what each line of their code does. So this line of code prints something to the screen. That's not really useful as opposed to a comment saying this block of code asks for the user's input and make sure it's validated. So it's either a 1 or a 2, something along those lines. And same thing, instead of saying this is a for loop that goes from 0 to 10, whatever, say this is a for loop that prints out the values of radians to degrees based on this step size that the user inputted or something like that. So that was one thing that I saw a lot. A lot of people just weren't having very meaningful comments.
Meaningful.c.
I'll see a meaningful.c. Also, as well with indentation, there were a few people who still aren't indenting their code properly. It should be something that we should all be fairly good with by this stage.
We did an example last week, didn't we?
On indenting, I believe we did. But essentially, whenever you see curly braces, everything inside those curly braces should be indented once. And all the indentation levels should be the same as well. So there's still some people that lost marks for that.
And not only that, the other thing to add, if the indentation's wrong, you're fighting against either Vim or fighting against Notepad++ because it does it automatically.
Yeah. So it should be some easy marks because it's all done automatic, but yeah.
I think I know how it's happening though, because
You're deleting
there's
it.
a couple of times where I noticed some wrong indenting in my code from when I'd had to go back and delete something, and I'd put it back in, and it didn't go in quite the right way.
Yep. Well, a good test of your code is, let me see if I can get something up. No, not the assignments. Oh, I've got so many assignments open. Something big. It's not big enough. That's not C. Okay. That's not C either. There's some of the solutions. These solutions are too simple. Let me open one of the solutions.
I'll just mention a quick one while you're doing that as well.
Oh, yeah, anything else?
Yeah, so I did see, I think, 1 or 2 cases of people using go-to statements. This should be something that no one should be using in this subject. For one, it isn't taught, and for two, it's terrible coding practice. So for your assignments and labs, if we see you using go-to statements, you're going to lose a lot of marks because you shouldn't be doing it. Terrible practice.
Until you learn exception handling.
Yeah. But yeah, for the moment anyway, definitely don't be doing that.
Can anyone else hear that mic banging?
Yes. It's Josh.
Sorry. It wasn't me.
Every time Josh is on Skype or something, he's throwing something at his mic.
Pretty much. Just. Is it worth mentioning the reports yet, or are you still going through code?
Yeah, you can reference them. Well, I'm just trying to get rid of all the stuff on my screen that shows all the other people's solutions.
Sure. So another thing with the reports, a couple of things I'll mention. Firstly, grammar and spelling is super important. As you go through later years, you'll really need to make sure that your spelling and grammar is up to scratch. We were sort of pretty lenient with this assignment, but as we go on, they should definitely.
Josh, do you want to also explain how to do a really short scientific report? Just them 4 steps.
Sure. Yep. So basically, and this was alluded to in the assignment as well, but there should be 4 key things in these reports. So 4 key sections. Firstly, yeah. 1 second. I'll just.
So we kind of wanted to see your scientific knowledge and you research how to write the report. So we left it a little bit open, but Josh will give you.
Have the reports been marked?
Yes, as I said in the announcement, it's part of the code mark. If you look into the code mark, right down the bottom.
Oh, okay.
It's the 3.
Alright, so I'm just going to share my screen.
Turn it into annoying to mark.
Am I on the screen?
Yes.
Hey. Alright, so these are the 4 sections you should be using on your report. So purpose, method, results, and justification. In this order too, because it makes sense.
And you shouldn't need a title one either. You shouldn't need to title them. It should just be one flowing thing.
So this is the order that makes sense. So first off, with purpose, this is just stating what the problem is, and it shows that you understand the problem of what you're actually trying to solve. So of course it makes sense. Firstly, tell us about what you're solving, what the problem is. Method, it should be the next thing you're talking about. So to solve this problem, this is how it works. So this is, this bit of code asks the user to get their input, validates it, all that sort of thing. So tell us about how you solve the problem. The results section should talk about, did it work? Is there any issues that you still have? So when you submitted it, there might have been something that was still not working. That should go in your report. It's part of what happened in your assignment and what your results were. And finally, at the end, just make sure you justify why you chose to do things the way you did. So especially if you've gone and, I don't know, you might have done something a bit differently, you might have had to do some typecasting to get stuff to work. Tell us why you did that. Because if you can think, if it wasn't us looking at this report, if it was someone else who had no idea what you were doing, they should be able to read your report and get some sort of an understanding of what the problem was, how you solved it, and why you solved it that way. There was some of these reports as well, like you could only really understand what was going on if you looked at the code, and that's something that a report shouldn't mean you have to look at the code to kind of follow it. Do you want to add anything else to that at all?
It's also good to have a title in your name and your student number.
That was a requirement, wasn't it?
What? Oh yeah, the name was, but it's also good to have a title. The title's always nice. A document looks really weird without a title.
Yeah.
We didn't take marks off for that, but it just looks weird. Okay, so I just got this up. This is the pressure one. So when you're scanning your code to check, I should put myself on the screen. So when you're scanning your code to check if your indentation's right, basically just look for your first curly braces, and it will highlight red. And if you go down the bottom, there should be nothing in between there. So there should be this gap wherever it's red. Then you grab your next one. There's nothing there between that one. There's nothing there between that one. Grab my next one. There's nothing there between that one. There's nothing there between that one, and there's nothing there between that one. And also you can see the little dotted lines. So you should be able to quickly check either by clicking on them or just looking if you've lost your indentation. Does that make sense? All right. Cool. And also, good work, Ila, for being the only person to get the challenge question working.
Come on, I got half of it.
Did you? No, in the assignment.
Yeah.
Oh, did you?
Yeah, I got the second half.
The second? No, lots of people got the second one.
Yeah.
How can you see if you have really got them full marks for the extra question?
I put all that information in the post that I sent out. Does not everyone read my posts?
I have.
Apparently not.
So if you go to week 4,
Yeah.
you go to week 4,
Mm-hmm.
and you go here, bonus task results, Bandura campus.
Oh, just a sec. Bonus task question.
Okay. Can you see it? Yes, no, maybe.
I can't open it because I don't have Office on my computer.
Well, you should be able to open an Office online. Especially if you're a student, you should have access to Office Online. If you log into your email, you have Office Online.
I might have to do that later.
Alright, so the next assignment. So I think we went through the background information last time. Fix this F up here. So this week we did this in the lab. So once you get your marks back, and we will double, triple check these, but you have the functions to do this. So if I need to do this here, I can now do something. Oops. What were your functions called, actually? I can't even remember. I think I wrote it
Complex addition, complex subtraction.
Yeah,
that's it.
pretty standard.
Cool. So now if I need to do something like this, where you've got an addition and a multiplication, I can do, and the division, I can do something like, zt equals, I'm just going to write com, what are we doing first? Let's say we'll do a division. Inside that, I'm going to call com sorry, z1 and z2, and then my second argument would be com, this would be multiplication, and the second one would be addition. So I can do things like this now.
That, just a note on that, that's going to be a lot trickier for them because they have 6 parameters for their functions.
Yeah.
So
But you can,
when you call commul,
oh yes, that's true.
That's not going to work.
Yeah, it's not going to work.
Good
point.
No, man. Stop confusing the students.
Sorry.
Thank you.
It's a really good point. Okay. But you have the functions. Start doing this. Okay. So I'll grab the functions up because I can't remember what they were, even though I wrote it. What lab was it? Lab 5.
5.
Ah, here we go. I've got it. All right. So if I needed to do this now, I probably should have checked. It would have been the smart thing to do. What have I done?
You just ruined it.
Yeah, I did.
You're using Photoshop now. Interesting.
Yeah. Except for it's being a pain. Photoshop's a little bit of a pain. All right, so I've got this equation here. So I've got, oh my god, nothing's working now. Sorry, I don't know why everything's decided to stop up. Let me unplug and plug it back in. What have I done? Oh, I just did the dumbest thing ever.
What was that?
I'm not even going to say.
That bad?
Yep, that bad. Alright, so if I want to do this, I've got ZT. So I've got ZT real, and that's a float. And I've got a float ZT imaginary. So now what I can do is perform each of these operations. Now you will actually need more variables because you'll need to store the result of this and the result of this, so we can have a temp variable in this case. So temp real and temp imaginary. What I might actually do to make it even simpler for now is change these two temp variables. Actually, change these to. I'll do it separately. Now, your problem is slightly different, so I'm not giving you the solution here, but just I think it's a good example. So we've got to calculate the multiplication. So we'll give a temporary variable for the multiplication to be stored, and then we've got temp add real. And then we've got float temp add imaginary. So this is starting to be quite large. The amount of things we can do to our function. So the first thing we're going to do, so we've got Z1 and Z2. So now we've got a million variables. Float Z1 real, which equals, let's say, 4. we've got float z1 imaginary, which equals 6. We've got float z2 real, which equals 8, let's say, and float z2 imaginary, which equals 7. Okay, so we've got a bunch of variables here because we've got 3 operations we need to do. So the first thing I'm going to do is the multiplication. So I can call my complex multiplication, and it was in 1 real, in 1 imaginary, in 2 real, so I can call z1 real, z1 imaginary, z2 real, z2 imaginary, and then I can send 2 pointers. So the last 2 are pointers, so I can send 2 addresses, and I'll send these. So this is temp multiplication real and temp multiplication imaginary. Once I've got the result of that, I can then do my addition and send the same thing, except for my last 2 variables are going to be temp add real and temp add imaginary. And then what I need to do for my last step is send, for the division, for the first one it's going to be temp multiplication real, then temp multiplication imaginary, then temp addition real, and then temp addition imaginary, and then I send these to my final result. So the address of z total real and z total imaginary. Does that kind of make sense? So to do that parallel, you'll need to do it in 3 steps. You've got to do the times, the plus, and then the division using the functions you're using. Does that make sense?
Yeah.
Cool. Alright, let me just...
You had a message on YouTube.
Yep.
So +1 for double pointers. I'm not sure if...
Oh, okay. +1. Oh, you want to know about double pointers. Okay, that's easy. All right, I'll just keep going through the assignment and then we'll cover that.
Cool.
We kind of already did double pointers before, but
Yeah, it should be earlier in the stream.
I'm happy to go over it again because it's fairly simple. All right, so you can use your functions to build these. The series are rather trivial, but these need to be done in 3 steps. You've then got your problem. So you're trying to create parallel or series circuit. You've seen this before. Follow the calculations. This is really great for testing your program because you can test it at each step and see what comes out. You've got a table. And as you can see, you only need to create these 2 functions as well as main. Now, this here requires malloc, which we'll cover later, so you can start doing this. And that will basically build your array, and we'll do that in the lab this week. All of this stuff is stuff we'll do this week in the lab. However, for here, we can start calculating the real and complex part for each component because now we know how to calculate impedance using our functions we developed from the labs. And printing the results, I think you shouldn't have too much trouble with. So is there anything unclear about the assignment that anyone's who started had? I don't want to give too much away, but I think you've got enough after this week's labs to pretty much do the whole thing. Right, let's go over double pointers again. Okay, so I'm going to create a program. So I've got int main, and I'm going to create my first variable as a car. The variable name is A, and I'm going to store 6 in it. Then I am going to create another variable, which is a pointer, and I'll call it pointer 1, and it's going to store the address of A. I'm then going to have another pointer, pointer 2, which is also going to store the address of A. Then I'm going to have another character, B, which will store 4. Now, this is the number 4. Okay, be aware of that. Then I'm going to have a double pointer, which is going to point, so this is pointer 3, and this is going to be the address of pointer 1. I'm then going to have another pointer, which is another double pointer, which is going to point at the address of pointer 2. I'm then going to make pointer 2 equal the address of B. Then I'm going to create another pointer, which is a triple pointer. This is pointer 5, which is going to be the address of pointer 3. Then I'm going to make another pointer. It's going to be a quadruple pointer, which is going to be the address of pointer 5. Then what I'm going to do is print all this out. So I'm going to print %d 1, 2, 3, 4, 5, 6. So %d, 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 %d. And then I'm going to print out star pointer 1, star pointer 2, star pointer 3, star pointer 4, oops. Also, Josh, do you want to just chuck the Hangout link again in the YouTubes?
Yeah, sure thing.
It's a bit easier to see the screen on the Hangout, I've noticed as well. If you're in the YouTube, you might want to join. And then pointer 6. So, as we covered earlier, let's look through this using our memory diagrams. So, the first step is character A. So we've got A, it's a character, and it's got 6 as the value. Our second line, we create a single pointer. So this is pointer 1, and it's of type caster. So it can point a single pointer. Check yourself on mute. 1, and it's of type caster. Mute. Cool. All right. So now this is all right. So now we have pointer 1, and it can point at a character. So as I said before, if you look at the star, everything before the star is what it can point to. So it can point to a car. So this here is pointing the address of A. And as we saw in the lab, we draw it like this. So the next line is pointer 2, which is a car star. And it's also pointing. It's also pointing to A. Now, the reason that we use double pointers is because I need to be able to point to these. So these themselves can point to A because it's a car, but a car star can't point to another car star. You need a double pointer to point at a car star. So we create another variable B. This is car, which is 4. And then we create a double pointer. So pointer 3, and it has the address. This is car. Oh my god. I'm not liking Photoshop very much. And this is pointing at pointer 1. And then create another one, another double pointer. And as we saw in the lab, each of these have a memory address. So this is now pointing here. So as you can see, anything, a car star can point at a car star. A car star can point at a car. And then here we change the pointer 2 to point at something else. So we now delete this. And it now points here from this line. And now we add another pointer, which is our triple pointer, pointer 3. So car, star, star, star. And that can now point at either of these two. So it can point to anything less the star. So car, star, star. So we're going to let it point to pointer 3. Then we're going to add another.
Matt, just a sec. Sorry for interrupting.
No, sorry. Yep.
So now pointer 2 is pointing to variable A and variable B, right?
No, just B. It can't hold more than one address. It can only point at one thing.
Yeah. Sorry.
Yeah.
Go ahead. Yeah.
It was pointing at that, and now we've overridden it. It acts like any other value. So if I have, oh my god, if I have int a equals 4, and then I go a equals 6, it's no longer 4.
Yeah.
It's the same as pointers. If I overwrite the value, it's no longer that old value.
Okay.
Yep.
Yeah. Thanks.
No, don't. Okay, so here, the last one we're creating is a car pointer with 4 stars. So there is only one thing here that it should point at, and that is one with 3 stars. So we point it to pointer 5. Yep. So basically everything should be pointing at something with 1 less star. It should be the same type, and it should have one less star. So car star 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 should point out a car star star star. Once again, as we saw in the lab, all of these are storing an address. So for our systems, they're going to be 32-bit long. Now, when we dereference, we need to go back a certain amount of spaces. So pointer 1, which is here, needs to jump back and grab the value that it is pointing at. So we've got this star here, which is saying dereference, which means pointer 1, go to that where it's pointing and grab the value. So it will go to this value and grab the value. So it'll print a 6. Pointer 2 is dereference one time, so it's going to go back 1 and grab the value. So it's going to print a 4. Pointer 3, the first star is the first dereference, so it'll follow this line and go back 1, and then it will go back 1 again and print the
Matt,
6.
can you please start again with the printf?
Sure.
Thank you.
Okay, so actually, what am I do? Rid of those lines. Alright, so the star is a dereference. So that's telling us how many steps to go back and grab the value. So pointer 1 has 1 star. So we go back 1 step and get the value, 6. So pointer 1, if we printed pointer 1 by itself, it'd print the address that's here. So it'd print the address of A. But we're not printing a pointer, we're printing a number. So here, it's going to print 6. The next one is pretty much the same, except for it's pointing at a different value. So it'll go back 1 step to here and grab the value 4. So pointer 2, dereference once. The next one has 2 dereferencing. So pointer 3 dereference once would be the value here, but we're not printing an address. So we dereference it twice, and we go here and grab the 6. The next one is pointer 4. So we dereference it once for the first star, and then we dereference it again for the second star. So we get 4. Pointer 5, we dereference it once for the first star, once for the second star, and once for the third star. And so we get a 6. And the last one is pointer 6. 1 star dereferenced, 2 stars dereferenced, 3 stars dereferenced, and 4 stars dereferenced. So we get 6, 4, 6, 4, 6, 6. Now, I just want to go back a step and get rid of all these. And I'm going to change it slightly. So what I'm going to do is delete some of these stars. So I'm going to delete that star, 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 and I'm going to delete that star. Actually, I'll delete all these stars. Okay. So now, because these pointer 1, 2, 3, 4, 5, 6 are pointing, well, these 2 are just storing addresses. So these first 2 we know have to be of type pointer. These 2, pointer 3 is a double pointer, so it means it's pointing at an address. So it's going to print out an address. Pointer 4 is also a double pointer, so we know if we only use 1 star, it's going to point out an address. Pointer 5 is definitely going to print out an address because it has 3 stars, and same with pointer 6, because it has 4. So now, pointer 1 and pointer 2, because we haven't dereferenced it, it's just going to print the value here, which is the address of A. Now I don't actually know the address, so I'm just going to write that. Pointer 2 hasn't been dereferenced, so it's just going to print out the value, which is going to be the address of B. The next one is pointer 3, and it's dereferenced once. So we're here, and we dereference it once. So we go here and grab its value. This value here is the address of A. So it's going to print out the address of A. Pointer 4 is dereferenced once. So it's going to grab this value and print out the value address B. Obviously, the address will be something big, but we don't really care what the value is.
Hey, Matt.
Yes? Now,
If you wrote B
Wait.
equals pointer 2, would the value at, would B's value be its own hexadecimal address?
okay, so let me just finish the last two, and then I'll go to your example.
Okay, sorry.
Right, you're right, don't be sorry. I'm missing a line there. So the next one is pointer 5, and we dereference it once. So now we are printing the value here, which is the address of pointer 1. And the last one is pointer 6. So if we dereference that once, we're grabbing the value here. So each of these stars, you just follow the line once and grab that value. So this value here is the address of pointer 3. Does that make sense for double pointers? Or triple, or quadruple?
Yep.
Yella?
Yeah, thanks.
Cool.
Jesus.
What? Okay. So your question was a rather dangerous question. So you're saying int star A, and then you're saying int B equals 4. And then
Yep.
what you want to do is go A equals B, or A equals 4.
Well, first I've got to have you've got to have A equals at B, and then B equals A.
Oh, okay. So you were trying
So
to
first so if A's pointing at B, and then you make B equal A, will B be its
Yes.
own address?
Can you stop for a sec? Okay, so you want to go explain again what you want to do?
So A points at B,
Yep.
and then B equals A.
B equals A.
Yeah.
Okay, so B is now going to hold an incorrect type, which you can do. However, as I said in the lab, this here could be a 32-bit number or a 64-bit number. Int can also be, or this could be a 16 or 8 as well if you go on smaller system. Ints can also be different sizes depending on which system you're using. Okay, that's the first thing. Now the second thing is B holds a value. Okay, so it's not pointing at anything. So even if you do store that value, which you can store that value, it's useless.
Yeah, but I was just thinking, like, if you printed out A and B, would they be the same number?
It depends what system you're using. Remember, it's system dependent.
Okay. Yeah.
So Matt, in this case, B will hold the address of variable B, right?
Yes. Now this firstly firstly the compiler is going to yell at you, but firstly this if you're going to do this needs to be unsigned. And secondly, if you use Windows or some different system, the values may not match because it'll be trunicated in the conversion.
Okay.
Because if the int only holds 32, but your address is 64, you get what I mean?
Yeah.
Now, I think the other question you were going, well, another good question is, I'll leave for you. Is that legal? Which I thought, that's what I thought you were asking.
Would that just be the same as A equals A?
Okay.
Wait.
This is not legal. Okay, because A can only point to inst. Well, it is legal in a sense, but it won't work as you expect because A can only point to ints, and the address of A is not an int; it's an int star, so it can't point to itself. Okay, so no, it can't point to itself.
Oh, okay, so that and following on from that, that would also mean you could never have like circular pointers that
You
point
can-
in a circle.
Yes, you can.
How if
Okay,
they can't point to higher pointers?
Okay, so you don't do it that way. Rather, this is with arrays. So you have, this is where you get to linked lists. You'll have a pointer that'll point to a structure that will point to another structure, that will point to another structure, and that structure will point back here. And this is called a ring buffer. Or a... Now, you haven't done structures yet, so you can't do that yet, but yes, you can do that.
Okay.
Okay. Is there any other questions for the stuff we've done this week?
I'm all out, I think.
Is there any questions from the lab that anyone had? All right. So what I might do now is quickly. What time is it? We've been going for 2 hours. Josh, is there any other quiz questions or something you want to go over, or is there something specific you want to go over?
Not that I can think of at the moment. From week 6 anyway. Hey?
All right. You have a 5-minute break. It's been 2 hours.
Do we need some elevator music?
Yeah, sure.
Okay.
I think what he meant to say was he's going to have a smoke.
Sounds about right. Hey?
Using my voice.
You're losing your voice. Talking too much. Can't be bothered playing elevator music, so sorry.
format. So in this case, are we going to have the same answer for all these options?
Yes, but it's confusing. Why?
Sorry?
Yes, we are actually, but it's interesting why. All right.
Because
Olivia.
we always get the starting address.
Yes. Now this is where it. So, Josh, are you back?
I am indeed. Oh,
Everyone
why
else
is
back?
that?
Oh, so we can
Yeah, I'm
start.
back.
Cool. All right. So there is a similarity between arrays and pointers. However, there is a big difference as well. Now, this is how I represent an array. The reason being is because ARR actually doesn't represent, when used, it doesn't actually work the same way as pointers and addresses normally would. So when you create this, there is actually somewhere in memory a variable that is pointing to the first memory address. So if I print ARR out, it should print A1. That makes sense logically, yeah? As with any other pointer, if we've got something pointing to it. So we're pointing to this first box of the array. Yep. It's the same as before. If I had a pointer here and I point it to this box, it's going to print the address of this one. Yeah? Now, what is interesting about arrays is that this here does not do what you think it would. So what you'd think it would do is return the address of this. Now, the reason there's no box there is because arrays don't act like that. ARR is actually, when used, not referring to this, it's referring to the whole array. And so, what happens here, it will also print A1. And this one is referring to the address of a IR index 0. So it's just going to print A1. Now, let's go back a step, but I just thought that's a really good example. So let's go up here firstly. So,
Did you say they'll all print A1?
yes, which is confusing. But let's go back a step so we can see why and see the difference between pointers and arrays. So when I create an array, when I create an int, let's say int A, and we have our big block of memory, as we saw on the board in the lab, that A could go anywhere, okay? And if I create int B, that B could go anywhere. It could go above. It's unlikely, but it could, okay? So this could be B and this could be A. However, with arrays, you're guaranteeing that they're contiguous. So if I do an array int, let's say int C2, they're guaranteed that the first element of the array will be here. So you got C index 0 here and index 1 here. So they'll follow each other. So that's one of the first things about arrays. Pointers, on the other hand, could go anywhere. Normal variables can go anywhere. Arrays are contiguous in memory. Okay? So let's look at something interesting. Now, when I declare an array, so if I go int d4, actually let's give it some values. Equals 1, 2, 3, 4. Then I'm creating my array, and it's d, and it's int, and then there's a 1, 2, 3, 4 here. Okay, now there is actually a pointer pointing to here, to this first one called d. This you will not know where it is or what it is, because arrays act differently, is what I was trying to get across from that last example. So if I do the address of d, it will actually return the address here, not here. Now, what we can do, however, is something like this. So I can do int star pointer e equals d. And this is perfectly legal because d by itself holds the address of this first one. So let's call this address 1, address 2, address 3, address 4. So now if I do a printf, and I print a pointer, and I print pointer e, it's now going to print out what? No one's going to guess. Come on, Josh, you know this.
A1.
A7.
A1.
A7.
Okay, because D always points to the start of the array. Now, what we also can do, because we know the memory is contiguous, we can do stuff like this. I can go pointer E equals pointer E plus 1. What would it print now?
A2.
A2. Because the memory is in order, it would print the next address. Now, it would actually be going up in 4s because these are ints, if that makes sense, because they're 4 bytes long. But you get the point. So this would actually be A5, A7, A9, not A7, A11, and so on. Okay. So we can do what is called pointer arithmetic with our pointers. So we can start iterating through our... So what I'm going to do now is delete all this, and I'm going to create a for loop. So I've got pointer E, and I'm going to create my for loop. So for, and this is part of the assignment. I equals 0. I equals 0. I less than 4. I plus plus. Then I have my for loop. And what I'm going to print is %d dereference pointer e, and then after that what I'm going to do is increment pointer e. So let me draw my pointer e here. This is pointer e, and it's of type int star, and it is currently pointing at this first one, okay, when it's here. So we're here right now. Does that make sense? Yes, no, maybe? Okay, then we create
Yes, thank you.
then we create another variable, I, which is an int, and it starts at 0. Now, 0 is less than 4, so it'll get here, and it's going to print the dereferenced print array. So what does it print? Oh, whoops. Got to put a possible set. What does it print? Follow the arrow and grab the value.
It'll print 1,
Yep.
then 2, then 3, then 4.
Then we get to the next part and we add 1 to our pointer. So now our pointer is pointing at the second address. And so we come back up. I is now equal to 1. 1 is less than 4. And so we print 2. And we continue going around until we get to 4. Now, this is really, really great, because now we can start working through memory. Now, what we can't do, however, is this. So we've already seen arrays beforehand, so we can do something like this instead, and that would have printed out the same thing. But what we can't do so we can do this, but what we can't do is this. Okay? Because it's declared as an array rather than a direct pointer, we can't increment it because D refers to the whole array. So D cannot be incremented. We can, however, do something like this. So we can't increment D itself, we can't change the value of D, but we can do this. So let's get rid of my for loop, firstly. That's my movie thing. Oh, no, it doesn't. Let's move this across. Alright, so if I did, oops, no, I did the same stupid thing I did before. So if I do D plus 2 dereferenced, what would I get? Does someone want to have a guess? Sure.
Something garbage.
No, we would actually get a value. So D currently points here, plus 2 because the memory is contiguous. D is of type int, and so we would print 3.
Okay.
Okay?
Yeah.
However, we cannot change D itself. So we can use D, but I can't do D plus 2. That would not work because then I'm changing the value of D. Here I'm not changing the value of D. Okay? The same thing if I did this dereference pointer E plus 2, what would I get?
You would get 3.
I would get 3 again. So this is very handy in terms of arrays because we can now do pointer arithmetic. If I just declared 3 variables in order, so instead of that, I did int A equals 1, int B equals 2, int C equals 3, and I did int e int star e equals the address of A, and then I did, instead of this, e plus 2. So this time I'm not using an array. So this time I'm pointing at A. So I create 3 new variables, A, B, C. And I create a pointer which points at this one. And it's called E. What would this give me?
Now it would give you something garbage, or it
Now
wouldn't
it
work at
would-
all.
Now it would give me garbage because the memory isn't contiguous. If you've got a lot of memory, it might actually be 3. Because you've got a lot of free memory, it may just allocate them in order, but you're not guaranteed with that, and it may just give you garbage, it may seg fault, it may cause problems. It's not always going to work, and it probably won't work in most cases. So you should never do that. If you're using arrays, then you can use pointer arithmetic or pointers. Does that make sense?
Yeah.
Yeah.
Cool. Okay, so we've got our array, and we know we can access all these variables, and we know we can point to each one of these individually. So I can also do something like int star e equals the address of D2. And then I can do a print, send D star E. And what would that print?
3.
Yes, 3. And what would this one print?
Oh.
Does that make sense, guys?
Yeah.
Yeah.
Cool. All right. Now, we're using C89 or C90. There's different versions of C. So we're using C89/C90, which is also referred to as ANSI C. And the most modern one is called C99. Now, if you did something like this, int n equals 4, and then you did int d, actually I'll give it a different name because I've already got d up there. If I do fn, will this work?
Yeah. I think it would.
So
In C99?
In C99, yes, it will work. In the system we're using, which is the older version, it won't work. Okay?
Why not? Why can't you have an array of n
Because
numbers?
because you're dynamically allocating memory. So C99 is doing this in the background, and it's not as nice. And it would make your life easier, but we want to see that you understand how the memory is working and understand good memory management. So
What if you had?
if you do this,
What if you had constant int n? Would that change anything?
no, because it's still a variable. However, you could do this. So in C89, oh my god, what is going on? I don't want that. And delete. So you can't do that in C90, which is the one we're using. But what we could do is go hash define big N is 4. And I could put that there. That is fine. Because this happens pre-compile time. So whenever it sees an N, it's just putting a 4 in there. Okay? But in C8990, which is the one we're using, you cannot have this lowercase n there or any other variable inside here. Okay? Now, if you had a look at the assignment, you would have seen the words malloc, possibly.
Dun dun dun.
So, this is fun. And if you understand pointers, it's not too hard. If you don't understand pointers, this can be really difficult. So this here is memory allocation. So we're dynamically, during the program running, we're allocating our own memory for contiguous memory. So when we create an int and all that, it's easy because the memory can go anywhere it likes. Okay, so if I do int a, I am dynamically creating that, but it's a single int, and so it can be stored anywhere. However, if we want contiguous memory, like an array, we need to use malloc, or the other one, which I don't use very often, which is calloc. But we'll leave that one for now, because I think malloc is better. Okay. So the difference between the array and dynamic memory is that now we actually need a pointer. So up here, we've still got our D, which is pointing to ints, and we've got 4 spots with 1, 2, 3, 4. However, here I'm going to create a pointer called E. And what I'm going to do is create 4 bytes of memory. No, I'm going to actually create 4, 8, 12, 16 bytes of memory dynamically. So what I'm going to do is go scanf, so let's say int w, and I'll do a scanf %d, and I will store the answer in w. So we'll create another variable called w, which is type int, and this is going to get the value from the user. So now the user can say how long they want their array to be. And as I said, you can't do something like this. Okay? Now in the assignment, you've got the same problem. You've got the user asking, how many components would you like? And so your array depends on the user during runtime. So how we get around this issue is we write E equals, we typecast this function because it returns a void pointer. We then call our function malloc. We then want to say I want 4 bytes for each int, so I use the size of operator. Then I'm going to times that by w. So what I am saying here is I'm allocating memory of size int, so that's 4. So I could actually write 4 if I wanted to. 4 times however many storage spaces the user wants.
Or components.
Components. So now, let's be the user. Luke, give me a number that's small.
3.
3?
300.
What? Oh my god. So we've got 3 here. I then create my pointer, which is here. And now I do this memory allocation. So I've got 4 times 3. What's 4 times 3?
Something.
7.
So I'm saying I want 12 bytes of memory. So 3 ints, which are 4 bytes each. The reason I use this size of rather than writing 4 is because if I use it on a different system, it will still work. So now what happens, this function here will create 3, which are all 4 bytes long. Now this is where you have to be really careful with pointers because it is just 12 bytes of memory. You're the one that's going to have to tell it it's always pointing as an int. Now, we've got these 3 new ints here. Now, they don't have a name, nor do they have a type. So my E now points to my memory, which is here. What's in them currently?
Nothing?
I will bonk you over the head if you say nothing.
But we don't know. We don't know.
Nothing is different from we don't know. Okay? Keep that in the back of your head. Because nothing basically means you rip the memory out. Even 0 is something. Okay, so this malloc has created 3 bytes of memory for us, and it's pointing to the first one. So now if I do something like, what have I done? Oh, I did the stupid thing here. If I do star E equals 4, what happens?
The first cell becomes 4.
The first one becomes 4. If after that I do E++, and then I do star E equals 6. Then this one would equal 6. Because E is an int star, it knows to go up 4 bytes each time. Now, good practice would be not to do this. The reason being is because E is your only link to this contiguous bit of memory. So it's good practice to create a copy. So let's say star F equals E, and use that one to iterate over your variables. Just because you want that starting address and you do not want to lose it. Because if you lose it and you're not tracking it, you may never ever be able to find that starting memory address again.
So what happens to all this memory when you stop running your program?
That is a really good question. So, this is where we end up with something called memory leaks. So, at the end of the program, any dynamic memory you allocate, you need to go free and then put your E in there. This frees the memory up. Because you've dynamically allocated it, and it doesn't actually have a name or anything like that, it still exists and will block your other programs from using that memory unless you free it. Eventually, it will get what's called a garbage collector, and it'll find it and delete it. But if you don't free it, you're blocking your computer. And so, when a good trial of that is create huge arrays using malloc on your computer, and just keep iterating the program over and over until you run out of memory.
I'm gonna not do that.
Okay. Sure. It's fun. It's fun for the whole family.
Be a hell of a prank on someone, though.
Yeah, probably just crash the computer. There's better things you can do than that.
So evil.
Oh yeah, we're recording. I'm not going to say them right now. I'll stay after. All right. So this time the user comes along and puts another value in. So Luke, give me a value.
6.
6. So our program would now create 4 times 6 spots in memory. Okay, so each one of these are 4 bytes, and now there's 6. So we successfully dynamically allocated memory. Remember, as I said, you can't do EW. Okay? Now, calloc. I hate calloc.
Calloc is fun.
It's overkill though.
Yeah.
Okay. So the other function you can use to do this is called calloc. The reason you may want to do this is because I don't know, you're paranoid about your memory not being initialized. However, if you're good at your memory management and know what you're doing, you shouldn't need it. So the other function is called calloc. It has 2 arguments rather than 1. The first argument is the number of elements you want to create. So in our case, this would be W. And the second one would be the size of the element. So this would be our size of int, or 4. Now what this does instead of our alloc, so int star E, let's get rid of this one. This one works pretty similar, except for firstly, yeah, you've got 2 arguments. So you're going to have to do the multiplication. But it also does something special. So it will point to 6 blocks of memory now, because you put in 6. 1, 2, 3, 4, 5, 6. And it will do one thing different. It will set them all to 0. Does that make sense?
Yeah, but why?
That's my question as well. That's why I think it's calloc. Okay, so that's calloc. It's got two arguments. The first one is the number of arguments. I mean, number of elements. And then the size of each element. Malloc, on the other hand, it will just be how many bytes. Okay? And the other difference with calloc, everything initialized to 0. Does that make sense so far?
Yeah.
Cool. Okay, so let me just check what else is for this week before I get into the full pointer arithmetic example, and then we might wrap it up.
Got some strings, I think, this week.
Hmm?
If I remember, we're doing strings this week.
I hate strings. Who uses strings?
Didn't you say in the lab that this version of C we're using doesn't have strings?
Correct. It has a special kind of string.
So, no real language has strings, really. But you'll see why. I might let Josh actually introduce that. Do you want to go through strings? And then
I'd
I'll
love
go
to
through,
go through strings.
and then I'll go through pointer arithmetic.
Alrighty.
I'll do an example.
Let me just bring up a beautiful paint document. Almost as beautiful as yours.
Almost.
Oh god, I looked away from the screen for like 5 seconds. What did you do?
Oh,
This is why we can't have nice things.
true.
Alright, can you see my screen?
Yep.
No. No, they can.
Is yours up? Is it upside down now? You're going crazy, Matt. You've lost the plot. Alright, so in C, we don't have a data type that's a string. So we have to be a bit clever, and what we actually do is we say that a string is the same as an array of characters. So what we can say, char name.
You're going to say main.
Main. So this is just one way we can initialize it.
But then don't you have to specify exactly how long the string is going to be in the beginning?
Correct, yes. So one way you can initialize your character array is if you do an initialization like this, it automatically works out how big your array should be. Otherwise, you can chuck a number in here, and that will be the length of your array. Now, at the end of every string, you'll have this character here, which is the terminating character. That's a number 0. What this does is it represents that this is the end of your string. So, for example, what this would look like is something like 1 M A T. So this would be an M. A. Actually lowercase, but so this is what it would look like when it's stored in memory. So we have this terminating character here that says that this is the end of our string. But yeah, essentially in C, if we want to use a string of characters, it has to be a character array.
But that means you can never change that string to another thing that's a different size.
So that's what we have is we have a lot of string functions, which we'll get into not this week but next week. And with those functions that we have, so we've got a library string.h, and inside there we have heaps of functions if we want to copy some strings, if we want to concatenate strings if we want to, I don't know, do all sorts of things. So we do have ways that if you want to, maybe I have this string Matt, and I have another string which is his last name, I can join those strings together and store that in another string or in another character array. So we do have methods to do these things, which you'll learn next week. And if we, hey, that's right. If we
do basic operations, if you want to show them.
You can, yeah, so this is just like any array. So I mean, if I wanted to work out what the third letter of Matt's name is, that's just the same as, you know, working out name of 2. Also as well, if I want to print out this character array, I can do that in a couple of ways. So I could either, maybe I want to print out, yeah, his third letter. I can print out just the character. What's that name? We also have another way if I want to print out the whole string. So what I can do is I can print out with this %s. So using %s, print out the whole string of characters there. It's a nice way that makes using these character arrays a bit more bearable instead of having to iterate through and print out every single character, using loops and all those sorts of things.
Do you need the string library to do that, or is that in the standard library?
For printing out, it's in the standard library. The string library contains functions for like copying strings, concatenating strings. I don't know. There's a bunch of functions. I can't remember all of them anyway. But yeah, for the basic stuff, so for getting indexes of Matt's name, printing out the name, all those other operations we have on arrays that we've been through, those you can all just do completely fine.
Okay.
Same as normal. So that's the main thing. And again, we do have this terminating character at the end of every string. And that's how it knows when to stop printing out characters. Because what this is doing is it's iterating through the array. And when it sees this, it knows that it's the end of the array. So it stops.
So Josh,
Yeah.
What is the length of the array?
So this array has 5 elements. So even though I'm just storing the name Matt, which has four elements, you could say, the array will actually have 5 elements because of this terminating character at the end.
Yeah, thanks.
Yep. Awesome.
Okay, what would happen if you say used pointers to alter the 5th piece of that memory?
Yep, so if I did something like, I don't know, I changed that to be another letter.
Yeah, and then you did the print S.
The printing, I believe what would happen is you'd be trying to access memory because it would see this is a character, this is a character, 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 character. So then it'll look to the next cell.
Yeah.
And who knows what's going to be there. So that's going to be one of those grey areas where you might get faults. You might get faults happening. You might,
Usually what will happen is you get a couple of characters to print, and then it'll segfault.
Yeah.
It'll keep going through memory until it finds somewhere illegal.
Yeah. So you're trying to access this next cell, but who knows what's in there if you're allowed to access it. So
sometimes it'll just print out heaps. Sometimes it'll print out nearly nothing. But you don't need pointers to change that.
Yeah, so we could just go name.
Could you just go char for blah blah? Oh, sorry, name for blah blah.
So you can do it like that, because again, this is just an array.
Yeah.
So all the stuff that we can do to normal arrays, it's just an array of type character, really, instead of integer like we've been using before. So those are the basics anyway. We'll get into more detail of different functions and how we can manipulate our strings next week. But for a basis, the main sort of points to know is a string is a character array. Every character array has one of these terminating characters at the end of it. If you try and print out an array that doesn't have one of these guys, you're going to get some weird stuff happening. So when you declare the array and initialize it, if you call it, say, Matt, for example, it'll automatically add in this terminating character to the end. Whereas if I said char name is, I don't know, length of 5, and instead of initializing it here, I might have, in the lines of code below, I might be saying name 0 equals m, name 1 equals a, name 2 equals t. I'd have to still say that name 4 equals that \0, just to make sure if I ever want to do this, I'm not going to get any weird errors happening. So it's something you have to be careful of when you're using these. That's why if you do initialize it at the same time as declaring it, it does it for you, which makes it a bit nicer. So, and just a question.
Yeah, I was. Oh.
Char name 6 equals Matt. What will be there at name 5 and name 6? Yep. So if you say, let me just extend the box. Get rid of that, and we'll add another rectangle. Yeah. Cool. So we just had a question. If we had the array size as 6 here, can't delete that. If this was a 6, so what will happen is the first 4 cells will be Matt. This cell here, do you know what the default is for a character? Matt?
No, I don't actually. No, it should be /0, shouldn't it?
It should be, yeah. So /0, and this will be /0. So this is the default for if there's nothing there. If you haven't actually specified what the next thing should be, it should default to just the terminating character. So that means that when you go to print out this string again, you've got more space in your array, but it's only going to print out Matt still. So say if I wanted to do later, though, I said name 0, 1, 2, 3, or if I said name 4 equals f, and then I printed this out, I'd print out Matt f, and then I'd stop printing stuff. So that would still work. We wouldn't be trying to access memory that we don't have access to, because our array size is big enough to still store an f here and still have a terminating character at the end. Well, does that answer your question there?
Cool.
Yeah, and the best way with these things is in the labs, just practice with these. They're not too bad once you get your head around them, how they're working, but they can be a bit of a pain because there's no real easy way to do it like there is in other languages. Ooh.
Do you want to just quickly? You have to go into detail, but you just want to show string compare.
Yep. So string compare is one of those functions that we talked about that were in the string.h. So in this library here. So what we do with string compare is, let's just say, for example, we have 2 strings. We have Matt and we have Josh. So char name 1 equals Matt. Char name 2 equals Josh. Right. So what we're doing when we use the string compare function, we're looking at 2 character arrays, and we're seeing which one comes first in the dictionary. So lexicographically is the technical term, but essentially we're just looking at which word comes first if we're looking for it in a dictionary. So again, the string compare is strcmp. This function is found in the string library, so we have to include string.h to use this. What we do is we give it 2 parameters, so we can give it name 1 and then name2. So what we'll be doing here is we'll be seeing if name1 comes before is equal to or comes after name2. So string compare can return 3 different values. So it returns a -1 if Matt comes before Josh in the dictionary. It'll return a 0 if these two things are equal. And it'll turn a 1 or a positive, should more correctly say it returns a positive number if Matt comes after Josh in the dictionary, a 0 if they're the same, or a negative number if Matt comes before Josh in the dictionary. So what you can do with these things here
When he's saying
is,
dictionary, he doesn't mean the actual dictionary.
yeah, it's just a way to kind of think about it, because lexicographically, no one really uses the word like in everyday language, but it's what it's called though in lexicographical order.
The order of the dictionary.
In the order of the dictionary, yeah. So if I was to use string compare, again, we'll just make a comment over here. So negative if Matt before Josh. 0 if Matt with Josh. Positive if Matt after Josh. And this is something as well. So like what we've done before when we're using integers, for example, we could say something like if, I don't know, a equals b, if we had something like int a equals 5, int b equals 5, we could use an if statement like this to check if these two integers were the same. You know, and if they're both the same, we go and do the stuff inside there. If we try to do something like this, if name1 equals name2, do you think if I did this, would this work? Does anyone have a go at answering that? So if I have my two...
It won't work, right?
It will or it won't, sorry.
Why?
Sorry, I didn't get you.
Did you say it would work or it wouldn't work?
No, it wouldn't work.
Why is that?
Can you clarify what you mean by wouldn't?
Sorry?
I said, Josh, can you clarify what you mean by it wouldn't work?
Yeah. So what I'm saying is, would I enter the if statement? If I declared up the top here, my name1 character array is Matt, my name2 character array is Matt. Would I enter inside this if statement?
No,
Why wouldn't I enter inside there?
because maybe the equals will check the address and the address won't be same.
Correct, exactly. So even though these two say the same thing, they're stored in memory in different locations. So we're comparing different memory locations, and of course they're not going to be the same. So yeah, this won't work as we expect it to. So if we want to compare if two strings are the same, we have to use this string compare, and then we can check if it equals 0. So if it equals 0, we know that the strings are the same. So to get this working as we want it to, we'd have to do something like that. Does that make sense?
Yeah.
Yep.
Cool, fantastic. So yeah, strings are a bit more of a pain, but they're good once you get used to them and you know what's happening. And again, yeah, so we have string compare, we have concatenate, we have copy, and there's a few others that I can't remember. Cool. Does anyone have any questions on strings at the moment?
Can you please tell me why strings are immutable?
Yep, so because, again, when we say our character array, name1, we're saying that we're giving it, in memory, what we're saying is we've set aside 5 cells.
So basically, it's the same reason as the arrays in memory, like any array. But yeah, Josh will explain.
Sorry, I'm doing this a horrible way. So what we're actually saying here is this character array is the same as sort of the first cell in this address. So when we actually do this, we're setting aside 5 cells in memory to store our character array. So what you're trying to say is if you try to say something like name1 equals, I don't know, whatever else, it won't actually work because when we talk about name1, we're talking about this spot in memory, which points to somewhere that has the letter M stored. And after the letter M, we have the letter A, T, T. So right now, this is what name1 looks like. Name1 is the first cell of this array. And we know that because it's a character array, we've set aside 5 cells to occupy where this address is pointing to. So when we talk about name1, we know exactly how big it is. If we try to say name1 equals something else, we're trying to say that, well, this is the address of name1. We can't really have it equaling something else because, I mean, it doesn't really make sense. We're saying that the first address of memory now, so this address of memory here, should be equal to another string. So if you're trying to do something like name1 equals Josh, for example, remember name1 is pointing to the first cell in memory. So when you try and make it equal to Josh, Josh is like some characters chucked together. And name1 is the pointer, essentially, to this first cell in memory. So we're not allowed to actually do this. If we wanted to do something like this, we'd have to use one of our string functions. And again, it's the same for other arrays. If this was an integer array, we still couldn't do that because this is where it is in memory. We can't tell it, go somewhere else just by saying equals Josh like this. Does that answer the question, or do you have any? Do you want me to clarify that a bit more?
I think that makes sense.
Makes sense? Awesome.
All right.
Cool.
I'll just add to that. Because C actually allows reallocation of memory, you can sort of get around. Things aren't totally immutable. However, it is dangerous programming. We have got a function called realloc, which reallocates memory, but it may not be in the same spot. So you can actually change the size of some things. Anyways.
So it's not good practice.
Generally, yeah. And that goes with any array. So if I do int array size 4, I can't easily change the size of it without using realloc. Anyways, I'm going to go back to your other question, which is really quick and simple. Can we have an array of pointers? Definitely. There's no reason why you can't. So on the screen here, let me just fix up the YouTubes. Where did the YouTubes go? Gosh, what did you do to the YouTubes?
I broke the YouTubes.
That's the quiz, that's the exam. Oh, there's the YouTubes. Alright, so can we have an array of pointers? Yes, there's nothing stopping us doing that. So in this example we've got up on the screen, I declare A, I declare B, I declare C, so I've got the boxes there, and then I create an array of pointers. So each of these here can now point to different stuff. So array pointer 0 is going to point at the address of A. Array pointer 1 and point at B. And the last one, yeah. Does that make sense? I think that's... Yellow?
Yeah. Thanks.
And you could do the same with double pointers, triple pointers, whatever. It's just a collection of the same type. You can also, when we get to structs, you can store arrays of structs. And you can also dynamically allocate pointers to. You can dynamically allocate. So I can do int star star array equals int star star malloc and so on. However, this is when you're going to get into two-dimensional arrays, which we're not going to do right now. And I don't think we're going to do it in this subject. We're going to do it a sneaky way instead. All right. Oh, I didn't really need to delete that. Have I got enough room? Yeah, I do. All right, so I'm going to write a small program. It's based on the, what's it called? The lab this week. So enter number of numbers. What a great sentence. So here, I want to basically get some values from the user. So I'm going to do this two ways. The first way I'm going to do this is by staying inside main. So as before, I did numbers equals int star malloc size of n times not size of int, sorry. Size of int times n. And that'll create however many the user wants. Often you want to put a limit on that as well. Just so the user doesn't enter something stupid. Now,
please allocate 50,000 int-sized pieces of memory.
That's fine. That's not much. So think about your hard drive, RAM, and stuff. Fucking got 8 gig of RAM. How many bytes is 8 gig?
Yeah, but with an int, you can't go much higher than that, can you?
What?
Well, you're asking the user to enter a number that's an int.
Okay, so if you have 8 gigabytes of memory, that is 8 with...
No. The memory bit I get. I was just saying that I don't know how high a number the user can enter.
Oh, yes.
Before the variable int can't hold it.
Well, then you use long. So longs can hold up to, let me check. Max size of a long int is, well, 64 bit anyway. So the max size a long int can hold, which is the bit number, is 42949679295. So that's about 4 gig of memory.
That's 2 to the power of 16.
Oh fuck it, it is too. No, actually, it's 92337373854775807.
Sorry,
Oh, shit.
that was 2 to the power of 32.
That's a big number.
This is a big number.
That's more than I have RAM.
Yes, definitely.
You're incorrect, Matt.
What?
Sorry. I lied to you.
That's 64. That's 64.
No,
64.
that's not 64. 64 is like,
Sine 64 is that. 2 to the power 63.
yeah. Oh wait, no. How many? Oh, sorry. The faces in the Hangouts are covering half of the numbers. That's why.
Them faces.
I could only see that looked like 9 million. Okay, that looks better.
Okay, so
My bad.
yes, the user could
Ignore me.
enter something stupid. That would be more memory than you have.
Now, please tell me there is some way that the compiler will return an error if that happens. The user wants to allocate more memory than the computer has.
No, it'll crash. It will crash. You may get a warning. There may actually be some protection, but it still should compile. There's no reason why it shouldn't. It's still a number. Anyways, so what I'm going to do here now is create another variable called, let's call it numbers position. And I'm going to declare it as an int star. Now, the reason I do this is purely because I do not want to lose the start of my array. Okay? So numbers always points to the start of my array. If I start changing it, I don't know where my array starts. Because remember, these don't have names. Okay, so in memory, you need to be careful. So, general rule, always try and create another variable for iterating. So now I'm just going to create another variable called I, which I'm assuming you've seen before, and I'm going to go I equals 0, I less than n, I plus plus, and I'm going to go, and this is directly going into the assignment as well. And I'm going to go printf, enter digit, and then I'm going to go scanf %d. Now, number position is a pointer. It's pointing to the first spot in memory of these. So I can just do something like this. Yep. And I can also do this because this will post increment. So when I've got the pluses on this side, it means that it'll add 1 after this has happened. Okay? So now, what will happen in my program is the user will enter a bunch of numbers, enter a number, let's say 4. It will create an array of size 4 dynamically, and there a loop and store each of these numbers. Does that make sense?
Yep.
Yep. It was we. Okay. All right. Because this will be the first address. Now, notice I didn't put the address symbol there because this is a pointer. So this will be the address of this first one. And then it'll go up 1, and it'll be the address of the second one. And it'll go up 1, it'll be the address of the third one, and the last one. It'll be the address of the fourth one. However many the user put in. I'm using n here, so it'll just keep going until it's full. Yeah? Now, what I'm going to do instead is move all this. This is lesser. I'm going to grab all that, and move it down. And what I'm going to do instead is now I'm going to create a function. So up top, I'll create my function prototype, and it's going to be called void get values. Oh, get numbers actually. Won't make it too similar. Now this is going to accept a double pointer, and I will show you why. Okay, so now what I want to do instead of doing all this in main, I want to get my numbers in a function. So what I'm going to do this time is write my function, a call, and I'm going to send the address of numbers. Now that is legal because int star is a int star star can point to the address of an int star, and then I just send n. Yep.
That won't compile
Why?
because the function's called getNumbers.
Oh fuck.
That'll do it.
It actually, I think it will actually compile.
You probably get another warning.
You get a warning and then it'll crash.
We haven't given
Won't it
it a
say?
function
Won't it say
definition anyway.
implicit declaration of get value? That's what I always get when I misspell printf.
Yes, but printf. That's a good question. I'll have to double check that.
You haven't got a function definition anyway, so it probably wouldn't.
Yeah. Okay, so get numbers. Int star star. See, I'll call it values. Fuck it. And int n. Now, I should delete all this stuff. Now in here, we have a double pointer to deal with now. So it's pretty much the same thing as before. However, just give me a sec. So let's make sure. So here, we need to dereference this values, and I'll show you why. Want some more room. I'm going to make this a little smaller. I want to draw the hopefully that's good enough. All right, so I'm going to draw the boxes. So we've got we've got numbers. We've got numbers, and it is of int star. We've got n, n, oh, whoops, n, which is of type int. Now, let's say you entered a value, let's say 3. 3 is a nice number. Then we get down to our function and we create 2 more. And this one's called values. This one's called n, and it's a type int, so that's a straight copy, so that's a 3. And this one's int star star. Okay, now the reason that we need to dereference these values when we're allocating memory, so if I do values equals int star malloc. Firstly, it won't work, but size of int times n. This won't work because values points to an int star. So I need to dereference this. Now we create some memory, some nameless memory here. And what is pointing to it, because we're changing the value at what values points at, this up here now points to this here. Okay, so when we get back into main, we now have, so if I just do return here, we now have our memory, and this will be gone. Okay, so if you are going into a function to allocate your memory, you need a pointer. Because if you try and allocate memory and leave the function, you've got no link to your memory. So if I just create, let's say I create another variable. So actually, let me delete some of this scribbles. So at the moment, I've got this link. Oops, that's not the eraser. Let's say I create another variable inside my function called int star x equals int star malloc 4 times zen. I'm just going to write 4 because I don't have much space. It will create a new variable called x, which is an int star, and it's going to point to 3 blocks of memory, 3 ints. Okay, so we've allocated that. But now when I leave my function, there's no link from main. So these are all have no link. Now, the other thing that is dangerous, these haven't been freed. Okay, so these are still owned by the program, even when you finish the program. So what we do at the end of our program, for if we do it correctly, so we don't do this line, never do that, we free numbers. Does that make sense? Why we don't do that?
Yep.
Because we just leave it in limbo here. If you did want to dynamically allocate memory and use it in the function, that is fine, but you need to free it before you come back to main. So I'd free x. So if you're just doing some operation inside the function and then it finishes, then you free x before you return main. Cool. I think that's enough.
Sounds good.
We've gone for long enough. Yeah, I think that's. We've covered strings, we've covered pointers for arrays, and we've covered malloc and calloc. Cool. Everyone can be happy. Happy?
Yeah.
Cool. Okay. I'm gonna kill the string.
Now it looks like a piece of toast.
It is a piece of toast. So stop broadcast.